I'll have Anna again for a second lecture. So please, Anna, go ahead.
Thank you. So I had promised that I would talk a little bit about the classification of these classical R matrices. So there is a theorem by Bethe and Drinfeld, and it basically states that like they kind of studied the pole structure of the R matrices, and they let me finish to write. And then they found that, oh yeah, sorry. And they basically found that all the poles of the R matrix are simple poles, but with this poles you can have some lattice, and then depending if your lattice is like 2D, for example, you have these R matrices of the elliptic form. This means that the matrix elements of the R matrix are all of elliptic functions, like Jacobi functions, and if it forms a 1D lattice, the R matrices are trigonometric. Again, in the sense that the matrix elements are of trigonometric form. This is wrong, trigonometric. And it's like 0D, then it's rational. And then there are very nice classified solutions taking this into account. There's actually a very nice paper that I always talk about from Jimbo, from 86, where he writes for all the algebras, these trigonometric ones, for all the algebras. So you have all these affine algebras like AN, 1, all these 2N, 2, like D. You have all of them, and he writes both classical and quantum, like the classical and quantum. So there is a very nice classification you can get for any rank. You can get there for any rank and just use, if you need some model for that that is associated to that algebra, just go there and take it. It's ready. It's very readable and easy. Like they're very explicitly written there, so it's basically no work. It's just copy them on the file and use it. So actually, these pole structures, this kind of a topology related thing, will be very important for the Chern-Simons talk that Sylvain will talk about. And yeah, depending on the boundary there, you have a different integrable sigma model. So I thought it was worth to mention this before we go into quantum integrability. So now we are going to quantum. Okay, so let's always, I keep writing small, right? Let me. Quantum. The first thing to say is that if you have a model that's classically integrable, it's not guaranteed that integrability will remain when you quantize it. So for many cases, you have to go in a one, I keep hitting this. So you have to go in a one-by-one basis. There are these classifications, as I said, like in Jimbo's paper, for example, that you know like exactly how their matrix generalizes. But if you have just some classical model, not necessarily you know how to quantize it. Okay, so this said, even with that, like there is a quantization of the R matrix. We know how is the quantum Yang-Baxter. I'll talk about this today, and what's the limit if you want to go classically again. And there is a Lax pair transfer matrix again, and we can construct the charges. So we can do these things in quantum mechanics as well. So, and in order to introduce these objects, I will focus in this XXZ spin chain. So I'll focus in this discrete system. I will focus on the periodic one, periodic. And so let's start with the Hamiltonian. First, just understanding what this means and why people are interested, and then we can go to a more algebraic construction. So the first thing to say is that this is a spin chain that's nearest neighbor. It's called nearest neighbor. And this is because we can write as something like this. So each side only interacts with the side just in its side. So like you have like side 2 will interact only with 1 and 3, for example. So this is usually called nearest neighbor. I probably lost an H somewhere. And okay, this n is the number of sides. So we'll have n sides in our spin chain. And then explicitly, it's written like this in terms of Pauli matrices. And this is the reason of the name XXZ, because if you look here, we have kind of the same weight in front of X and Y. So we call it XX because they are equal, but Z is different. Just to mention there is also the XXX, which is when this delta goes to 1. So it's some kind of homogeneous one. And but there is also the XYZ. And the XYZ, you have 2 deltas. You kind of have a different, coefficient in front of each of X, Y, and Z of these parts. So as I said, these sigmas are just Pauli matrices. And when you see these sigma i's, you can think of that thing I explained at the beginning for tensor product. So this sigma I is just to put sigma in the I side. Oops, side. Side. And then you put identities everywhere else. So you have you can have a identity. So you can construct it explicitly if you want on Mathematica very easily. But the problem is that if you look, these things, like each of these matrices are 2 by 2. So this Hamiltonian kind of grows very fast with the number of sides. It grows exponentially. So this, it's a 2n by 2n matrix. So in practice, if you try to just diagonalize it in Mathematica, you would not go very far. If you want to describe like a system with, I don't know, 10 sides, you already, is already hard. So it becomes very hard to diagonalize. And today I will explain how to construct these Hamiltonian and the other conservative charges related with this XXZ. And then tomorrow I will explain another way to diagonalize these charges, because that's a bit easier. Depending on the model, it's you can go much further diagonalizing it, which is the Bethe ansatz. But today we'll focus on constructing this algebraic structure behind this model. One thing I forgot to say is that I said that there was this classification, and if you look, there are matrices, this XXX is of regular type, so you kind of have some regular matrix. This XYZ is the elliptic one, and the XXZ, that's the one I'm talking about, is trigonometric. So just in this simple model, you already see kind of where this kind of classification enters. But let's study this Hamiltonian just a little bit more. So let me. And yes.
Yeah, I have a question about the classification, because you just said that XXX corresponds to rational and so on. But how does this link to what you said about two-dimensional lattice, one-dimensional lattice, or zero-dimensional lattice?
Oh, it's not. I'm not even that was related to the poles of the classical R matrix in principle. So that classification came from classical integrability. So Bethe and Rll, when they did for these classical R matrices, from the part I know, maybe they could utilize, but I don't know. But like here, you cannot see. I not even wrote the R matrix yet, but yeah, you cannot. It's just that you can actually you can see in some sense that XXX, the R matrix is only depends on the spectral parameter. If you go to XZ, you see that it will depend on some isotropic parameter eta that is related with this delta. Yeah. So it's one parameter, and if you go to the elliptic case, you depend on two parameters. You have some eta and some and one extra.
Ah, okay.
So I think in this way you can see. I don't. So just about this. There is this extra dependence on the quantum at quantum level. At the classical level, this kind of doesn't explicitly appear like this. It's more about the pose of the.
Okay, thanks.
Okay, so this Hamiltonian is a toy model of magnetism, and you can see these like in a simple way, just by computing the ground state. Like, so if you can take like 3-4 sides and compute the ground state, you see that what happens that you have two options. For delta bigger than 1, what happens that your ground state will be what we say it's ferromagnetic. Oh, I forgot to say something important first, sorry. So since these are Pauli matrices, we are with we are trying to describe a spin chain here, and I said it's periodic, so it satisfies this. This is equal to this. And also I'm assuming J, for all the discussion I'm doing now, I will assume J bigger than 0. Everything kind of about the ground state kind of changes if you choose your J smaller than 0. Okay, but then you, like, if you construct this Hamiltonian for, let's say, 3 or 4 sides, what you see is that, so for delta bigger than 1, it's ferromagnetic. Oh, I forgot again. What I wanted to say is that since we are describing this spin chain, like this closed spin chain, so I'll have n sides, and in each side, we can put a spin up or a spin down. And then, so we will see that the ground state, it's when you have all the spins up or all the spins down. So you can see this I left as an exercise, but you can see this very easy, just computing the Hamiltonian and diagonalizing it for a few sides. But something very interesting happens, and it's a bit more complicated when delta is smaller than 1, because you find that your ground state is actually like some coefficient times this plus, I don't know, this. The point is that you have your ground state, it's the one that kind of your spins try to be anti-aligned, kind of so this is what's called ferromagnetic when they want to be pointing in the same direction. And when they want to point in the opposite direction, it's anti-ferromagnetic. So for even number of sides, you see that this is really like the most general combination with half of your spins up and half of your spins down. So you have really half, but for odd, you have two options. You have n-1/2 up and n+1/2 down, or the other way around. So yeah, this is like in this lecture, we'll focus on this one to teach better ansatz because it's much easier. But you can see that when you go to higher sides, this is a mess. Like it's not something you can play very easily because it starts to like your ground state starts to be huge because you need to take into account all the possibilities to put like half of them up or down. So yeah, it grows very quickly as well. So yeah, we'll focus in this ground state for the purposes of this talk. But I thought it was nice that you can already see from here that you can study some kind of magnetic models already in this at this level.
If you take delta less than 1, but you switch the sign in J, do you get the ground state again, the spin aligned, or it doesn't work?
Oh, if you switch, I think you just find the opposite kind of
okay.
When you need the eigenvalues.
Okay.
Yeah, so it's you just have to fix one choice and then you can do it. It either changes delta as well, like or you have to choose then like delta will be smaller than 1 for the
it's okay. Just you switch.
It's them. Just yeah.
Okay, thanks.
Yeah, so. Okay, but even from the classical part, we were always focusing in like that integrable models have all these towers of conserved charges. This is true here for the quantum side as well. And as basically everything we try to do from classical to quantum, it basically you go from like a Poisson bracket to a commutator. So here, instead of wanting that your charges will be in involution, now we want them commuting. So you have this is equal to 0. And what we'll do now is to construct all the formalism to reach this point of having the conserved charges in a systematic way. So the first thing we would like to define now is the R matrix, the quantum R matrix. And so here we'll always use this diagram. Like every time you see two lines crossing, you can, in a diagram that I will draw, you can think like two lines of the same color, you can think as the R matrix. And then this depends like it's which space you are, for example, 1, 2 here. And so this is Z1, Z2. And this R matrix is defined, it acts in two Hilbert spaces. So it maps two Hilbert spaces in two Hilbert spaces. And it's defined as the solution of the quantum Yang-Baxter equation. So the quantum Yang-Baxter equation is R12. R23. Let me put the comma here first. Again, as in the classical side, we start with this general case. And then this can be represented in pictures. Oh, here I forgot again. See, here, comma. Okay, we are starting with this general one, but for exact z, so this is the most general Yang-Baxter that you can write in quantum mechanics, but for the exact z, actually we are in a simpler case. We are in the case of difference form, where we can write this as the difference. So this is again called like a difference as an R matrix of difference form, and when this is not satisfied, it's called non-difference form. Actually, like all the classifications, most of the cases that are known are of this type. There are a few famous cases that are not, like Hubbard model and like the R matrix of n equals 4, like that appears in n equals 4 supreme mules, like this ADS5 by Weiser. But most of the other models that we know, like they are, oh, there's Potts model as well that I remember now, but like there are not many models that I can name that are of this non-difference form. Most of them are actually of this form. So I'll focus on this today, but many of the things I will say actually generalize very easily for the other.
So small question. So, so you say mostly they have different forms. So are there some models where the spectral parameter has some physical significance, where that would explain this difference form, or is there no explanation? It's just something fundamental.
Usually difference form are... Oh, sorry. So you can associate difference form with to be a model relativistic. So all the models actually that are non-difference form, like Hubbard and this one in ADS, when you construct the dispersion relation, it's not p quad p squared plus m squared square root. It's something more. Oops. So you lose. If it's non-difference form, you lose immediately. You cannot have this relativistic property. So what I'm not sure if it's all the difference form ones are relativistic or not, but but you break immediately relativity if you go to non-difference form.
Thanks.
Okay, so for the purposes today, I will just write this as difference form. So I will write again. But something similar to the classical, oops. Before I was writing with the minus, now that I need to put the minus, I put the comma. See? Minus Z2. So like in the classical case, we can just do this shift in Z1 and Z2. So when we are describing these difference form models, usually the Yang-Baxter only depends really into spectral parameters because the Z3 disappears. So, but when you are in non-difference form, you cannot perform this trick, so you always depend on 3. And now, oops, here we can write this in a schematic way, this Yang-Baxter as this equals to so 1, 2, 3, 1, 2, 3. And this is basically like every time the lines cross, you have an R matrix. So it's, I still wrote here, we can put a 0, this one equals to 0. Because now I eliminated the Z3 already. But yeah, like every time you have the lines crossing, and this is basically the statement that you can move these lines through each other and you have the same result. So any of these 3 lines that you try to move through each other gives the same result. So if you try to move them, you can and they give you Yang-Baxter. So it's just a schematic way to draw. But tomorrow at the end, if I have time, I will give all these things an interpretation with some scattering matrices. And then this will, I think, be a bit more intuitive. Okay, so let's. Okay, one thing when we quantize that we want is that we want to be sure that the classical part is okay. So what I will do now is to show how to recover the classical Yang-Baxter starting from the quantum one, just to make sure we are doing everything accordingly. So what you do for that is you define let me just this is the classical one. And what will happen is that you recover Yang-Baxter when you compute to order H squared. So what we'll do now is, let me write Yang-Baxter here so we can see it, because I will forget that 3 that we don't need. And please feel free to interrupt me anytime. I didn't say, but it's fine. I'll be happy to reply if I know. So okay, so I will call we'll start opening the right-hand side, the left-hand side here. So left-hand side. And this, if you look Yang-Baxter, it kind of like the quantum one. This doesn't happen for the classical one actually, but the quantum one, you can always change your R's by some overall function, and it continues to satisfy because you have the same 3 matrices multiplied on both sides. So your Yang-Baxter is always invariant under multiplying your R by some function. So I will forget this kappa just to make it quicker to write, because it will be the same in both sides, because we have exactly the same spectral parameter dependence in both sides. So this kappa will not make a difference. Okay, so let's start. So R12, we'll write this as 12 plus 8 bar, R12 of Z1 minus Z2 plus order H squared. Okay, so in order 0 in H bar, you only have this when the identities all multiply themselves. So it's just in order H, we'll have when each of these multiply only identity, like it's only the term that these multiply identity and identity, or these might multiply the two identities, or the same with these. So this just gives our, this doesn't look like an R. This is R12 of Z1 minus Z2 plus R13 of Z1 plus R23 of Z2. Okay, now it comes the order that we want. So we will have H squared when we multiply two of these R's, right? Like the H bar is only multiply the R. So if you have these two, or these two, or these two. So with these you can write these multiplying these, or these multiplying these. We could have the H terms of H bar squared here as well, because we want this H multiplying identities, but you see that for the same argument that these will cancel in both sides, that would, so I didn't write because it will be long. But if there is any doubt about that, when I finish the calculation, please ask me. And now we do the other side. The other side is 2, 3. Okay, so now we again, in order 0, we have just these identities. In order 1, we have one of the R's multiplying all the identities. So we have A23 of Z2 plus and now we need squared. We have again the product of two of them. So first we multiply these. And then we multiply this, either these or these by the R12. So this gives R23 Z2 plus R13 Z1 multiplying R12 of Z1 minus Z2. Then we have. Okay, so let's look what's happening. So at order 0 is just identity in both sides. Identities all so. In order 1, we have this here, that's here, this here, and this. So it cancels as well. So the first one that doesn't cancel is 8 squared. And then if you look, this minus this is the commutator, right? So it's R12. And this, with this is another commutator. I put wrong. So it's that side first, so it's 1, 3. Which is exactly the classical Yang-Baxter. So with this, we see that we can recover the classical limit when we take this expression. And also here you can see why you cannot oops. Yeah, you can see why I keep doing that. You cannot just multiply the classical R matrix by some function. Like if you just do that for this spectral dependent classical Yang-Baxter, because you have a sum here, it will not just go overall as an overall factor. And so this is a property that you lose when you go to classical, like in quantum, like the quantum R matrix. There are many transformations you can make that will keep Yang-Baxter invariant, but when you go to classical case, you lose many of them because of the structure that's not just a product in both sides, that things kind of. Are there any questions?
So there is a question, and the question is there any physical significance of H bar? For example, what would be the classical version? It has H bar small for XXZB.
Usually, like I will write now the quantum R matrix for the XXZ, and then I will write to you I will write the quantum, and then I will write the classical limit so I can show what happened. But it's when you see at least this classification, I don't know what's the meaning, but when you see, especially classically, I don't see the meaning, because when you have the quantum version, you have this for XXZ, you have this eta that it's some, I don't know, an anisotropy in your chain. For all the trigonometric have these. And then you have to, when you go to classical, you do this expansion and this disappears. So it's kind of like the H bar, like this is directly, when you see in the way, at least Jimbo writes, he relates this H bar directly with this eta directly with H bar, and it disappears. So I will show like the quantum R matrix will depend on these. When you take the limit, it disappears. So you have only the spectral, the usual spectral parameter. So the answer is like no. Classically, I don't see what H bar kind of. So
perfect.
Okay, thanks for the question. So let's. Now that we did that, I think we go to Lux. Let's see if I didn't miss anything that I wanted to say. Oh, just again, like I think I mentioned this quite a few times, but I really recommend you, if you are not familiar with all these sites and all this notation, to play a bit on Mathematica and by hand as well. Like I left many exercises that are not very hard. They are just to get some practice with these that I think are quite useful. So if you want to work with these someday, I think it's quite useful to have some, because after you do just a few, you get it becomes very easy. So it's just a bit of practice. So let's talk now about these lags. Oh no, I just said I would say this. Okay, so for the XXZ, our R matrix is given by sinh of Z plus eta and the rest is rho. So this R matrix is the quantum, a quantum version of XXZ. Let me write the classical. I think it's this. So here we'll see another property that we immediately miss. We kind of lose when we go from the classical to quantum, to the quantum to classical, is that this is what we call regular. It means that R of 0 is just that permutation that I defined at the beginning. This is very important if you want to construct a spin chain that's first nearest neighbor. So yeah, usually if this doesn't happen, I just don't know how to do, because I will show later how to construct the Hamiltonian and the charges, and you see where this enters. And yeah, it plays a big role there. And if you see here, it even kind of explodes if you put z to 0. You have to be careful. And so I left an exercise, like I put all the, I forgot to put on Slack, but I will put now after the class, after the lecture. I put all these, all the generalizations of XXZ so XXZ is A11, this is a fine algebra. And then you have all these.
Question. In the quantum R matrix, do you want sinh or cosh? I'm asking because to me it seems that R of 0 is not permutation.
Sorry?
I don't see how R at z equal to 0 is permutation.
Oh.
So I was wondering if sinh should be
because
cosh.
it's proportional, sorry. It's because if you put here to 0, because it's sinh, this becomes, sorry, it's right here, R of 0. This is
Okay.
sinh of eta 0, sinh of eta 0, sinh of eta. It's, yeah, I should have been more precise here. It's just it's apart from a function. It always, if you don't, it always can be up to one overall factor. So yeah, I didn't write the explicit form of the permutation when I gave the introduction at the beginning this morning, but if you for like Hilbert space with dimension 2, it's just this. So you lose some properties when you go to classical. It's not a problem. I'm just pointing out that there are some properties that are not the same. And you have to be, I highlight these also because in the exercise, when I was preparing the lectures, I had problems when I was trying to, I just took Jimbo R matrix for quantum, and I was trying to recover the classical one that we said was correct. And I was getting the wrong thing, because when you have eta, what you actually do is you have a function here, you have identity, but you have another function here. Okay, eta. So you write an expansion in eta, and you get so it's like eta plays the role of your H bar here, but you need to put something here. If you just want to put the R matrix directly, it doesn't work. And this is because for the classical Yang-Baxter, you have to choose the proper factor. Otherwise, it doesn't work. So I left as an exercise to do this for this half spin half XXZ that I'm explaining, but also to do spin 1. But in the file, I just left the general one, so you can play and with any rank if you want. Sorry, I replied, right? You were happy? Oh, okay. So, and these are matrix has also another property, which oh, somebody raised his hand.
Sorry, may I ask you, what is the meaning of eta? The physical meaning of eta? From the Hamiltonian, I can read it or not?
They called anisotropy at the level of the Hamiltonian. It's how it's like to going from if you take it to 0, is like going from xxz to xxx. So you have that Hamiltonian that has all the factors the same in front of the. So they call it anisotropy, but actually, it's related to it when you talk about quantum groups, and these things is related to that as well. Usually exponential of eta is the Q when you do these quantum groups. I don't know if you are familiar with quantum groups, but at this level, yeah, like it's because we will see that it's there is a direct relation between eta and that delta in the Hamiltonian.
I see, okay.
So
okay. Is there...
this is what I think I can say about. I don't know where is the camera. Actually, I'm looking to the thing when I'm talking.
Yeah, sorry.
Sorry. So it's
okay.
It's okay?
Yeah.
Okay.
So, sorry, is that some special case when eta is equal to 0 that you have that at the value of z equals 0, you have this 0 value of the R matrix. Having the cinch, I see that when eta is equal to 0, you have that the R matrix is equal to 0.
I'm not understanding what he's saying.
Yes, you said that R evaluated at 0 is a permutation.
When
is
z equals to 0 is permutation. When
yes, but if also
you wanted to know what I can do to eta in principle that.
Something special happen at that point. I see just actually, there what is a cinch of eta times.
Actually, something kind of special happen when you choose the spectral parameter as some specific values of eta. Like if you choose z as minus eta, let me see here. I think it's z equal to minus eta. You can have a matrix, you reduce the rank. So there are some more advanced things you were doing in integrability that when you fuse the Yang-Baxter, you fuse, like you kind of put two spaces together. I will not enter on these, but you only can do that. You use this, exactly this point where the rank of the matrix decreases to do this kind of trick. So there are some things, but there is nothing very intuitive that I can say, I think.
Okay. Thank you.
Okay. I have just a quick question because I missed what you said about a n of 1, and also maybe you can explain the notation. I don't know.
Oh, okay. Yeah, this a is just like usually the way mathematicians talk about SL.
Yeah, and the one?
The one is just means that it's affine. It's just that this is kind of a quantum version of, you start with a Lie algebra, and this is kind of the quantum version of the Lie algebra. So in practice, it's like the Lie algebra with some Lorentz series and some grading. It's like when you put all these three together, you have, it's hard to explain without saying many things, but that's, so yeah, usually you have some grading associated to these and,
yeah, okay, that answers.
Yeah, and like all the ones that are like these with these indices, like all these affine ones are related always to trigonometric R matrices. So this is it's kind of what's in Jumbo paper.
Okay,
okay, some other property that this R matrix has that will be useful for us when we are proving that the generating functions of the charges commute is that we have unitarity. So we have, and I changed this indices now from like 1, 2 to alpha beta because it will play an important role when I define lax. But because I need like 2 notations then, but okay, so the property is basically that you have these. Let me. And this has some function. So this will play this unitarity. And this will play an important role in the discussion of the charges. This is a good point to have a break if people want, because then I start lax and then it's a completely new thing. So maybe 3 minutes. We can come back in 55. 5:50. Okay, so let's continue. So the next object I would like to talk to you about is the lax. So this is the object that we use to compute the charges and to construct the Hamiltonian. So we usually write it as with two indices. Oh, first of all, you can interpret these as just some transport between like two sides, adjacent sides. So this is +1. But when we talk about to really use it to construct this monodromy and the transfer matrix, like to construct the objects to get these charges, we write it, we use some tricks. So we use two indices. And I think in the notes I put these with the, when I made like just some graphical representation, I just put this as black and this is blue. So it's again two lines crossing, but you consider a different kind of like these two spaces have a different nature, you kind of can say. And the point is that this is the one we were always talking about. So when we were describing a spin chain, we have n sides that are physical. So we have n of these Hilbert spaces. So our spin chain acts on n of these, and these are called physical spaces. They are the ones that we are described by this index I. But we introduced a new one, which is called auxiliary space. And this looks like something we just randomly put it now, but actually when it's a trick, like when we trace it out to compute the generating function of the charges, it will disappear and only the physical spaces will remain. So it's just a trick to kind of connect all the sides of the spin chain. I know it looks confusing, but I hope it will become clearer until the end of the lecture. So this L is a solution of an equation very similar to Yang-Baxter. It's called Rll Equation. It's like this. This can again be kind of be put in like a graphical representation as I probably did not draw it very well, but it's similar to Yang-Baxter. But now we have two auxiliary spaces, so I'm putting them in black, and then the physical one in blue. And this is equal to move this basically. So we have again, but now this here. This is very bad drawing, but it's like, and you see if you treat these spaces here as just some physical spaces, or this one as auxiliary, like if you kind of treat them all in the same nature, for L equals to R, this is Yang-Baxter. It's really Yang-Baxter. It's just, so what happens is that what we use today is actually when L is equal to R, but we will write it in a fancy way that's very useful, but it's in practice, it's just R. But you can have other representations when you have like, I don't know, some algebras of higher rank, you can have like, okay, for XXZ, both, I forgot to say, but okay, so this acts in two spaces, and so in two different ones. So L alpha 1, for example, acts on like some V cross H. So this auxiliary space. So okay, so I said about the, let me see what I forgot. Okay, so this is the most obvious kind of choice, but when you're higher ranks, you can have, for example, like for XXZ, this is just a C2, and this is a C2. We are just considering them like with the same nature, and we are having L equals to R. But when you are in like other kind of algebras or other models that are bigger, you can, for example, choose them with even different sizes, and then you have to do all those tensor products accordingly. You have to think a little bit, but you can have different representations. So different L's are just different representations of your algebra, but usually these are the objects you need to construct the spin chain. So for these RLL, so for XXZ, I will write this L in two ways. One will be useful for today and the other for tomorrow. They are exactly the same. It's just a way to say things. So the first, X. Okay, let me explain this first one before we go to the second. So when we write this way, what we are thinking is that we are putting this auxiliary space, that in our case is a C2 at the very beginning of the spin chain, and then we are putting Hilbert, like physical Hilbert spaces in the rest. So from that thing I explained at the beginning, if you want to write this sigma alpha X, now we put this, so here it goes from 1 to n, so we have n. But so here you can call alpha, or I don't know, 0, if it will help you not get confused here. But it basically you put them on the first side. So in practice, this is sigma X on this, and the rest will be identities. But when you go to this with the side, this index J, you are in the physical part of the chain. So you start to count 1 from here. This is just what I'm saying. So when you construct on Mathematica, you can choose to put this auxiliary space anywhere, but it's convenient to choose it at the beginning or of the end, or at the end. Otherwise, you get it's much more messier to do the calculations. But at the end, it's physically the same thing, because we'll trace it out at the end, and it will not contribute. Okay, so if we want to do these, we have identity on the 0, on the alpha 1, identity on the 1, and then sigma on the 2, and then the rest is identity. And this is very convenient from what we'll do today, because if you see, it's already in a very similar form to the Hamiltonian we had at the very beginning. with all this sigma alpha and like all the construction will kind of force us to have j plus 1 kind of thing, but this looks a lot like an object that if you apply a derivative and multiply by something, you get this Hamiltonian. So this is very useful for what we do today. But for what we'll do tomorrow, there's another way to do that. That's to write as a matrix. So the spaces in this matrix is somehow, so you see that the alpha will not appear here explicitly. So, and then you have this sinh. Plus sigma z. Here you have sigma minus, oops, j. So this is convenient for the Bethe ansatz, as we'll see tomorrow, because it's already in a form that we can trace immediately. When we are in this kind of format, if you want to trace alpha, you have to, like on Mathematica, you have to do some, in a general way, you have to do some tricks, like you have to do, it's not hard, it's just you need more, but for the Bethe ansatz, when you do all these products, you see that the trace is really, you're already in that space in the sense that the trace in that space is really just to take the trace in the matrix you are looking at. So you can just sum the elements on the diagonal. So this will be very helpful for the Bethe ansatz, but not too much for today. So maybe I will write again tomorrow. But if you play with this on Mathematica, be careful, because the sinh function of Mathematica will not give you the correct answer because we have matrices inside. So you have to define your own kind of sinh function using this matrix exponential. So you just, you can use this command to, you cannot immediately apply.
There is a question. So the question is the Pauli inside sinh? Okay, actually, I think you just answered.
Yeah, yeah. If you wanna know how to do it by hand, it's just to expand and resum at the end. You expand Taylor series and then you. So it's really. But Mathematica can do this for you if you define like this sinh of z as this matrix exponent of z minus the same with minus z divided by 2. You define this function for Mathematica and then you can apply it as many times you want. So this is the way to do it, because otherwise none of the results I'm saying will be true, because Mathematica just treats it in the wrong way. Oh, and okay, this sigma plus and oh, the advantage also here, not advantage, but here, since you cannot put this in a matrix in the sense that this space is already there, this is something acting only on those n Hilbert spaces. So this sigma j is really, you have some sigma at the position j and the rest identity, but in total you have just the n physical spaces. So this is another way to do it. It's different, but I left as an exercise to you to show that the origin of our matrix and these things are all kind of equivalent. It's a nice exercise to get some practice this kind of calculation. I find all these things quite nice and fun to do it, so I keep suggesting, but yeah, if you have any problems from the beginning, even on the basic exercise, just talk to me, because then if we solve, we can solve the rest of the exercise and go ahead with the things. Okay, so let's now define the monodromy matrix. So we are in a periodic chain, so let's, okay, this, yeah, ignore this sentence because it doesn't play a role here. So it's, but this is, you usually start from n and go until 1. you do this product. And if you remember, we had represented these L's as just two lines crossing. So here, if you see, we are keeping this auxiliary space all the same for all of them, and we are kind of going through the chain. So this T can be represented as, we have this space alpha, and then you have all the physical until you reach the first one. So you can represent it in this way, and it's useful even to check some properties that I will talk about now. And this order is not very important. Like, you have to follow an order, but you could have started from 1 to n. We'll take the trace later, so it will just connect anyway. Like, this direction doesn't change your Hamiltonian or anything. So yeah, you can do as you want. And now we have the first property we need to, because we want to construct this object, this transfer matrix, which generates all the conserved charges. And we want this transfer matrix to commute. So in order, the first thing we need, the first relation we need is this Rtt relation, a bit similar to what we had for the, let me write here so I don't erase this. So this is basically R alpha beta, Z alpha Z beta. And this is true if RLL, the one we defined that was very similar to Yang-Baxter, if RLL is satisfied. Let me show you. So we will do this calculation just for 2 sides, but it generalized very automatically, as you see, for more sides. So it's just so I can do it reasonably quickly. So let's do alpha 2. And alpha 1, so 2 sides. So let's start with the left-hand side. We have now we have the alpha of Z alpha here. So let's put the indices. And then we have with the beta, so it's just changing all the alphas by betas. 2. And then I didn't talk much, I just realized at the beginning, but if you have 2 objects that act on completely different sides, they always commute. And this is because if you had, for example, A1, you had A cross many identities. And if you have B2, you have one identity and then B. So when you multiply these by these, you have A cross B with 1s everywhere else. But when you multiply these, because it's A times 1 and 1 times B, you always can do these if the products, matrix products make sense, you always can do these. But when you define these times these, it's again 1 times A and B times 1. So every time you have something that is in different sides, it commutes. So this means that we can just, if you see here, it acts on alpha here and beta and here 1 and here 2. So we can just switch completely these 2. Beta and alpha 1. But this is exactly the left-hand side of RLL. So we can just switch completely the order, and this is again the left-hand side of RLL, but the first one was with index 2, the physical index 2, and this is with the index 1, but it's the same. And now again, I did something wrong. Oh, here it was 2 and 2, and I changed it to a 1 somehow, but it's a 2. Okay, so we can now switch these two, because again, they act in different sides. And then if you look, this is it was, yeah, I erased it, but oh, it's here. So look, so we have these. So we can just rewrite, and here we have d alpha of z alpha and r. So we just found the other side. So this Rtt, so this is the right-hand side. So it's this Rtt is true. And if you can see, the type of calculations we did is just keep switching these spaces and use RLL many times. There is no reason for this doesn't work with more sides. It generalizes immediately. You can do for more sides if you want to practice, but you see that it generalizes easier. But you can do it pictures actually. So what was T? T was a line with many lines crossing. So when we do it schematically, so we have all these L's, the product of L's. So we will draw it here as making a curve, but you see why. And this we'll call alpha, and this is beta. So it's just a way to write the left-hand side of Rtt, and then you have until 1. And then what we are doing, actually every time, and this is in each of these is like, this is L alpha n, and this is L beta n, because it's, what we are really doing with that calculation is that we pass this through here. Every time we use RLL, we pass one of these lines through. So if you pass all these lines using RLL, and then you are left with, oh, and 2 lines crossing is there, so this is there. So schematically, it just means you are passing these lines one by one through the, using RLL. And then you get this. Oh, okay. I think. Okay, now that we have Rtt, So let's write it here because we use it again for the next proof. And so there are many small proofs here, but they are all very straightforward. And what we will do now is we will claim that the generating function of, oh, this should be Z, of our charges is to trace over this auxiliary space. And if this is true, then from these, we will obtain the conserved charges. But this has to be true, because we write this as an expansion, and then if this is true, that it's true for any for each of the charges. This is similar to the classical in some sense. It's very similar. It's basically the same thing, but here we have the commutator instead of the Poisson bracket. But this, it's again very easy to prove. So let's start with just the first side of the commutator. This is trace of alpha, T alpha, trace of, oops, T, beta, Z, beta. So they are in different spaces. I can put this as a trace in both spaces and put them together, because each of them act separately, so we can always do that. And then, if you remember, we had unitarity. So we had that R, we can write is proportional to identity. I will forget all these constants just to avoid make mistakes now, but they are, so we will assume we will put a proportional here. And so this is proportional to 1, so I can include this as some identity here. So this is just this, right? So I can write as this other one. And now we use the cyclicity. We have the trace in both spaces, so we can use the cyclicity of the trace for both of them to pass them here, and then they together become a 1 again. And then we have an equal again, because the factor we had the 1 over, now we cancel it back. So this is trace of alpha beta. And this can be separated again in trace of beta of T. Oh, I call it 1 and 2, and then I'm calling all alpha and beta here. So here is alpha and here is beta. Sorry. And here is Z alpha. So we just recognize it again. So this shows that the transfer matrix commute. So we only use it in this unitarity and the RTT for this. I have 4 minutes, right? Okay, so the conserved charges. will be just acting with these derivatives in the log of T of Z, and then send Z to 0. Okay, like these, I don't think I will have time to open the examples. Maybe I will show just the first one, and then tomorrow I show the Hamiltonian. But, and okay, I can go from, it's just an integer actually. So you could ask why I put this log here. It's because it's periodic. If you try to compute the Hamiltonian on the charges, they will not be local if you don't have this log. When you have this log and you apply derivatives, like you apply the first derivative, you have like something like t minus 1. And then you have something like this when you derivate, and then send Z2. And the things that appear here appear in a very nice way, exactly to cancel everything that you don't want in the other one. And then things rearrange in a way that you can sum. So you have this Hamiltonian for two sides, and then you only have to sum this Hamiltonian for each pair, basically. So it's this is for locality, but this will become clearer tomorrow when I do the explicit case. Okay, I have 2 minutes. Anybody has any question?
In the derivation before, at some point you ask, you use the cyclicity of the trace for the R. So why can you not use cyclicity just on the T? Is it because it only has one index?
It's a very good question. It's because this is a very misleading notation that everyone uses. So T of alpha here doesn't mean that I put T in the side alpha. It just means that I have all these products or this with this extra index here. This is not the same. It kind of, it's just a very misleading notation. So you have, so we cannot pass through to, because if you have Bethe here, let's just do two sides. And Bethe. Even if we had the same spectral parameters, let's, if you cannot pass these two because you have to pass a two to a two. You cannot, like this has like different alpha and beta, but has the same two, so they're not the same size. So this is just a very bad notation that everyone uses. So I try to just keep the notation of the, and I don't know a better notation anyway, but this is misleading because it's the only place that this index doesn't mean that you're putting in that side. So that was a very good question. Thank you.
Yeah, okay, thanks.
I have a question, because you said you need the log to avoid any non-local charges. But you have some system where you want these non-local charges, because
then you don't put.
Okay, so
they will still be conserved charges because you prove that your transfer matrix will commute. So, and for open spin chains, it's local without the need of this. So for open chains, the log is not there. But for closed, we need the log to have locality. But if you don't want locality, everything still works in the integrability sense because the transfer matrix is commute. And I've talked far from the microphone, so I'm not sure anybody else heard the question. Yeah, heard it.
it was clear online as well.
Okay, great. Okay, so I think that's it for today. And then tomorrow I will finish and show you how to compute the Hamiltonian and the momentum, and then do the Bethe ansatz. Thank you.
Very well. So many thanks to the lecturers of today and the participants.